All right, the last homework is homework 24. It just has two topics, both are having to do with sign tests. It says a coin-operated coffee machine was designed to discharge 8 ounces of coffee per cup. In a test of the machine, 17 cupfuls of coffee were drawn from the machine and measured. The number of ounces discharged for each cup of coffee is 7.5 ounces, 7.75, 7.89, 8.24, and so forth. At the 0.05 level of significance, can we conclude by using a sign test that a mean discharge of a cup of coffee from this machine differs from 8 ounces? Perform this hypothesis test by completing the table below. If necessary, consult a table with critical values for the sign test. It is going to be necessary to consult that table, so first thing you're going to want to do is print it out. I'm going to hop over to Alex. On Alex, when I have my question there, you'll notice here when it said if necessary, consult the table, that you can click on that. And so I'm going to go ahead and open that up. It's going to bring up a table with the critical values. My table with my critical values, I have my numbers in there, and here my numbers from 8 to 25. It's either going to be a one-tailed test or a two-tailed test, and then the appropriate critical values that I want to check my level of significance will be in there. And so you'll want to print that table out. I've got it printed to use for reference here, but you're going to want that table so that when you work the problems, you can look at the table and find those values. So I'm going to leave that up there for a minute, just when I hop back and forth, it erases what I have. So on here, we want to check to see if it differs from 8 ounces. So our HO, our null, is going to be, is it equal to 8 ounces? Our alternative one, it is not equal to 8 ounces. What we're going to do is assign a sign to each of those numbers. Is it above 8 ounces, it'll be positive. If it's below 8 ounces, it'll be negative. If it's exactly 8 ounces, it's going to be 0. So 7.65 will be below, it's going to be negative. 7.75 will be negative. 7.89 will be negative. 8.24 is above, it's going to be positive. 7.92 back to a negative. 7.73 is a negative. 7.72 is a negative. 7.73 is a negative. 7.75 is a negative. 7.93 is negative. 7.73 is negative. 7.80 is negative. 8.22 is a positive. 7.75 is a negative. 8.00 is exactly 8, so I'm going to give it a 0 number. 7.91 is a negative. 7.70 is a negative. So anything that's below 8 is going to have a negative. Anything above 8 is going to have a positive. If it's exactly 8, we're going to give it a 0. So what we're going to do here is we want to know how many values in our table do we have a plus or a minus. In other words, we're going to ignore this one that was exactly equal to 8. So now we have n equals 16 because we originally started with 17 numbers on our list, but we had to take one off of our list. So on our table, we are going to look at n being 16 and that it is a 0.05 level of significance, and because this is a not equal, we're going to use, or an equal and a not equal, the two-tailed test. So that's probably going to erase all of my writing, but I'm going to flip over to that table just so you can see where we get that number from. And so here's my number. If I look at 16, two-tailed test. So here's my 16. I'm doing a two-tailed test with a 0.05 level of significance. So my critical value is going to be 3. Okay? If I go back to my pluses and minuses, which I might have to rewrite again. We'll see here. Yep. Again, if I just quickly do this, negative, 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 positive, negative, 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 positive, negative, 0, negative, and negative. If I count up my negatives and positives, I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 negatives, and 1, 2 positives. The value of the test statistic is going to be whatever number is lower. In this case, the positive number was lower. It's going to be 2. My critical value is going to be that number we just looked at in the table. When we had n equals 16 at a 0.05 two-tailed test, we got 3 for our critical value. So, if the test is less than or equal to the critical value, we are going to reject the null. If the test is greater than our critical value, we are going to accept the null. Remember, we have to do the equal there when we are going to do the less than or equal to. So in this case, comparing my two numbers, 2 is less than or equal to 3, so we are going to reject the null. The null again was that it was exactly equal to 8 ounces. The alternative one then is that it's not equal to 8 ounces. So this is my true statement. That's the one that's not true because we rejected the null. So can we conclude that the medium discharge of a cup of coffee from this machine differs from 8 ounces? It's not equal to 8 ounces. That's the true statement. So yes, we can conclude that. Whoops, I skipped the decision. My decision here is in the drop down that we're going to reject the null. It'll either say accept the null or reject the null. In this case, we're going to reject the null. And so does it differ? Yes, it does differ. So basically just going to put your signs in there, count them up. How many negatives, how many positives, whichever number is lower is your test statistic. We're going to look up the critical value on the table. We're going to make the decision. If it's less than or equal to, we reject it. If it's greater than, we accept it. And then we can answer our question. So if we look at number 2 here. Number 2 says, a random sample of 21 male students at a local university was selected. Each student reported his height in inches and his height was measured. The results are as followed. So here's the reported height, here's the measured height, here's the difference in what they really reported. So we're checking to see, well, how close are they to what they thought they were? At a 0.5 level of significance, can we conclude by using a sign test that there is a difference between the reported height and the measured height of the male student? So, on this one, is there a difference? We would say that the null is does it equal 0. If it's 0, they were exactly right. If there is a difference, it's not going to be equal to 0. So are we checking, were they exactly right or were they off by a little bit? Again, we are going to use our sign test and we're just going to look here at our numbers. Since we're comparing it to 0, if it's negative, it's going to be negative. If it's positive, it's going to be positive. And if it's 0, we're going to cancel it out from our list. So in this case, we got a negative, a positive, a positive, a positive, a positive, a positive, a positive, a negative, a positive, a positive, a positive, a positive, a negative, a negative, a negative, a positive, a negative, a positive, a negative, and a negative. We don't have any zeros in this case. So we are going to use all 21 for our n because we didn't have any that were exactly equal to our null. So n is going to be 21. Again, we're going to use a 0.05 level of significance. We're doing a two-tailed test. Again, I'm going to erase this so I can go back and look at my table, but we'll put those back in there. So again, when I look at my table, oops, I got to go over here. On my table, if n is 21, if I could draw straight, and I do a 0.5 level of significance on my two-tailed test, my critical value is going to be 5. I go ahead and look that up right away. My critical value is going to be 5. So back here, my critical value, hey, I put my stuff back. All right. Now it's not going to let me write. Oop, maybe it's going to let me write. I'm getting there. All right. My critical value is going to be 5. We figured that out. If my thing does not want to work right, you give it a second. See if I just use my pen tool. Nope, still doing the same thing. 5 doesn't want to work. Let me clear it and see if that works then. There we go. My critical value is 5. Again, for the value of my test statistic, I'm going to count how many negatives and how many positives. I erased all those, but we can still tell from the numbers. You probably have them written down, I hope. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 negatives. Positive numbers, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That should add up to 21. It does, because n was equal to 21. So in this case, my test value is the lower of those two numbers. 9 is the lower of those two numbers. So 9 is my test value, 5 is my critical value. So I am going to go ahead and compare those two numbers. 9 is greater than 5. Since my test value is greater than my critical value, I am going to accept the null. So that's my decision, accept the null. Now again, on this case, it erased what I had written down, but our null said we were exactly equal to 0. There was no difference. Our alternative one, it's not equal to 0. There is a difference. So in this case, we're accepting the null. This is my true statement. That one is not true. So can we conclude that there's a difference between the reported heights? No. We're saying that it is exactly equal to 0. There's not a difference between their heights, or at least not enough to say at a 5% level of significance that there's a difference. So if we're going to accept the null, we're not going to have a difference. If we reject the null, then we say, yes, there is a difference. All right, one more of these. A toy manufacturer claims that the median amount of time that their top-selling toy captures children's attention is greater than 30 minutes. To test this, the sample of 11 children is selected and their attention span in minutes while playing with this toy is given below. So 20.8, 33.4, and so forth. At the 0.025 level of significance, can we conclude that the median attention span for playing with this toy is greater than 30 minutes? So on this one, it's a little bit different because now we're doing a greater than. Again, when we do our null and our alternative one, the alternative one is going to be greater than 30. The null less than or equal to 30 because the equal has to go in with the null, right? Way back we started all this stuff. We said the equal always has to be with the null one. So in this case, we're just going to do a one-tailed test. So we're going to look and compare for 30. We've got below 30, above 30, above 30, above 30, above 30, exactly 30. We're going to take that off the list. Above 30, exactly 30, we take that off the list. Above 30, above 30, above 30. So now, how many do we have on our list? 1, 2, 3, 4, 5, 6, 7, 8, 9. n is going to equal 9, 0.025 level of significance. This is going to be a one-tailed test since it's a greater than instead of an equal to. So you're going to consult your table again. I'm going to zip over here, bring up my table, and so we said n was equal to 9. I got to erase that so we can see what's going on. N is equal to 9. We were doing a one-tailed test at a 0.25 level of significance, so our critical value is just going to be 1. One-tailed test at 0.25, so 1 is our critical value. Going back over here then, we know our critical value was 1. Whoops, let me get rid of this stuff. The value of our test statistic. So again, this one was less than 30, more, exactly, more. We have one negative, and 1, 2, 3, 4, 5, 6, 7, 8 positive. That was our n equals 9, how we got our numbers. Our value of our test statistic is 1. I always take the lower of my 2 when I count up my negatives and my positives. I'm going to compare those values. 1 is less than or equal to 1. Notice the equal sign in there. When we said it was less than or equal to, our decision there was to reject the null. So again, I got to think about my hypothesis. My alternative one was the greater than 30. My null was less than or equal to 30. This one is the not true one. So this one is the true statement. Because we decided we should reject the null since 1 is less than or equal to 1. We're going to reject the null. So can we conclude that the medium attention span for children playing with this toy is greater than 30? Yep, it is greater than 30 is the true statement. So yes is going to be the answer to the question. Okay, 4, 5, and 6 is the Wilcoxon signed ranked test. And in this case, again, there is a critical table value for the Wilcoxon signed ranks test. You are going to want to bring that up and print that out. Again, I may have a one-tailed test or a two-tailed test, and they gave me some different values I can check. And so I want to make sure I have that table also. So make sure you log on, get that one printed out so that we can consult it as we work through these problems. I closed my Word document, so now I got to bring that back up here. So, day 24, if I go back to problem number 4 where I left off, it says, a random sample of male students at a local university was selected. Each student reported his height in inches, and his height was actually measured. The results were in the table below, so this is very similar to what the previous one looked like. He reported 74, his actual measured height was 72.4, a difference of 1.6. So at the 0.05 level of significance, can we conclude by using the Wilcoxon signed ranks test that there is a difference between the populations of reported and measured heights for male students at the university? Complete the table as we did before. So we are going to start off with, on this one, by doing our positives and our negatives like we had before. Here, positive, positive, exactly 0, positive, positive, negative, positive, 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 negative, positive. So in my table here, I've eliminated one of my things because it was exactly right. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. N is going to be 14 when I use my table. Again, on this one, we want to conclude, is there a difference? So my null is going to be, is it equal to 0? My alternative one, is it not equal to 0? If it was exactly equal to 0, there would not be any difference. So, on these ones, what we're going to do, if I'm going to figure this out here, is, first thing I'm going to do, I'm just going to go ahead and look up my number from my table and find my critical value, because that way, when I have to erase it and put it back, it'll make it easier than doing that. So I'm going to go ahead, just clear this out, go over here to my table. We said that n was 14. We had figured out n was 14. We are doing a 0.5 level of significance. Since it's an equal and a not equal, it's a two-tailed test. So two-tailed test at a 0.05 levels of significance means my critical value is going to be 21. So I'm just going to go ahead and look that up first before I do all the rest of my work. Otherwise it erases. So 21 is my critical value. I'm going to close that. Go back over to my paper. 21, that's the value we looked up. So on this one, what we're going to do is order all our numbers in order. However, we're going to pretend that they're all positive numbers instead of having both positive and negatives. So I want to rearrange this in order, and so I would have the smallest number here, not including the 0, is the 0 or 0.3. So I'm going to have 0.3, did that one, which was positive. I'm looking here, I have another 0.3 that was negative. I'm looking over here, I have another 0.3 that was negative. Let's see, my next number, 0.05. I have a 0.5 that was positive. I have another 0.5 that was positive. Don't have any more 0.5s. I can see the next number I have is 0.6. So I have 0.6, which is positive. I don't have any other 0.6s. 0.7, I have a 0.7, which is positive. No 0.8, so now I'm going to go to 0.9. 0.9 is positive. And then I don't have any 1s. I have my next number looks like a 1.2. So I have a 1.2, which is positive. I have a 1.3, which is positive. I have a 1.6, my next number. Yep, 1.6, 1.7. That's positive and that's positive. 1.8 and 1.9. Positive and positive. So I put my numbers for my differences all in order, ignoring the sign. We're just going to assume they're all positives there. So, and again, I leave off the zeros when I do that. What I want to do is average my numbers on here if they're all the same. So in this case, I have 3 of them here that were all 0.3. My ranking here, I didn't rank yet. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. We had 14 numbers. That was our value for n, was 14. So in this case, instead of saying this is 1, this is 2, this is 3, because they're all the same, I'm going to average them and give them all the same rank. 1 plus 2 plus 3 divided by 3 would give me 6 over 3, which is 2. So I'm going to give all of these a value of 2 instead of saying 1, 2, and 3. On these ones have a 4 and a 5. 4 plus 5 divided by 2 would give me 4.5. So on these ones, I'm going to both give them values of 4.5. Then I had all my numbers, the rest of them were different. So if I have any numbers that repeat, I'm going to take their ranks and average their ranks out and give them all the same ranking. So all my 0.3s are going to have a rank of 2. All of my 0.5s are going to have a rank of 4.5. and then I just keep going on my list. So, in this case, I look at how many negatives and how many positives. I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 positives, and only 1, 2 that were negative. Just like on the previous sign test, I always go with the lower value. I'm going to go with the lower value. I had 2 of them that were negative. My 2 that were negative were these 2 right here. The 0.3s, right? We had a negative 0.3 and a negative 0.3. In order to find the value of my test statistic, I'm going to add their 2 ranks together. Well, their 2 ranks for both of these were 2, so 2 plus 2 gives us 4. Now that I did all that work, I can make my decision. My decision basically is the same way we did before. If my test value is less than or equal to my critical value, I reject the null. If my test value is greater than my critical value, we accept the null. So in this case, my test value is 4. That's way less than 21. We're going to reject the null statement. Again, it erased, but my null statement was there a difference? So my null statement was, are they equal to 0? My alternative one is it's not equal to 0. We're going to reject this one, so this is my true statement. At the 0.5 level of significance, can we conclude there's a difference? They're not equal, so yes, there is a difference between the populations of reported and measured heights for my male students. So again, if we do accept the null, there is no difference. If we reject the null, then there is a difference, just like on our previous ones. So on the rank sign test, the key, putting my numbers in order, ignoring the sign on them when I put them in order, and then if I have some values that repeat, I have to average their ranking and give them all the same ranking. If they don't repeat, then they just keep their regular ranking and you can go from there. Alright, so number 5, same kind of thing here. The following table shows the monthly return rates for 2 mutual funds during 11 randomly chosen months. At the 0.2 level of significance, can we conclude by using the Wilcoxon signed ranks test that there is a difference between the populations of Fund A and for Fund B? Again, asking, is there a difference? So my null is that it's equal. My alternative one, it is not equal. So on my table again, I am looking here, and can we conclude that there's a difference? And so we're comparing it to 0. We're going to get rid of any zeros off our list, so I'm going to get rid of that 0 there. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 numbers left in my list. So n is going to be equal to 10. Since I'm doing, is there a difference? At the 0.02 level of significance, we're doing the two-tailed test. And I'm just going to go ahead and look up the critical value first before I do all the sign stuff, because I have to erase everything when I go look up my critical value. So n is 10, 0.2 level of significance when there's a two-tailed test. And so if I bring up my table, there it comes. N is 10. There's my row for 10. I am using a 0.02 level of significance on a two-tailed test. So my critical value there says it's going to be 5. My critical value is 5. So going back to my problem, my critical value is 5. We said our null was equal, our alternative not equal. Now I'm going to figure out my signs. I have negative, positive, negative, 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 positive, we're not counting that one, and a negative. I've got 2 positives and 1, 2, 3, 4, 5, 6, 7, 8 negatives. We said on the rank test, we have to put them in order from smallest to largest, ignoring the signs on there. So if I do those, I've got my smallest number 1.2, 1.2, 1.2. Both of those are negative. My next number there, I'm going to have 1.8 and 1.9. 1.8 and 1.9. 1.8 was negative, 1.9 was positive. My next numbers there, cross them off as I go, so remember I use them, putting those in order. I'm going to have a 2.4 and a negative 2.4, so 2.4 and 2.4. One of those was positive and one of those was negative. Then I'm going to have on my thing a 3, just a plain 3, and then I have a 3.4, and then I have a 4.3, and a 4.9. I'm going to erase all my X's now that I have my numbers written down. And again, we're going to get rid of the 0. So now we're going to rank them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We had earlier said that when we looked up in our table, n was going to equal 10, right? We have 10 numbers on our list. If any numbers repeat, we have to average. So in this case, these two repeat. 1 plus 2 divided by 2 gives us 1.5. Each of these are going to have a value of 1.5 instead of giving one a 1 and one a 2. And then right here, our numbers repeat. So 5 plus 6 divided by 2 is 5.5. Each of those numbers would have a value of 5.5. The rest are all different, so we don't have to worry about averaging their values. When we do our signed rank test, we're going to use the one that has the lower number of positives or negatives. So in this case, we're going to use the 2 that were positive. So we had 2.4 and 1.9. The ranking of my 2.4 was this 5.5 that we averaged out. The ranking of my 1.9 was the 4, because we didn't have to average that. So for our test value, we're going to take the 4 plus the 5.5, which is 9.5. 9.5 would be the value of our test statistic. So we take the ranking of each of our numbers that were positive, because that was the lower number of positives that we had. We had more negatives than positives. So the 2.4 had a rank of 5.5. The 1.9 has a rank of 4. If I add those together, 9.5 is my value of my test statistic. So now I compare those values. 9.5 is greater than 5. Since my test statistic is greater than my critical value, we are going to accept the null. That's my true statement. Accept the null is my decision. So if we're going to accept that they are equal, can we say there's a difference? No. That one was not true, that there was a difference. And one last one. The following table contains the first exam score and the second exam score for a random sample of 12 students in a large college class. So first score was 75, second one was 80, difference of 5, or negative 5 in this case. First one was 76.5, the second one was 84.5, difference of negative 8, and so forth. At the 0.5 level of significance, can we conclude by using the Wilcoxon signed rank test that there is a difference between the populations of the first and second exam scores for this class? So again, we're checking, does it equal 0 or does it not equal 0, which means there is a difference. If I look at my table, I do have one that's exactly equal to 0. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 is going to be our value for n. Oh, why did it decide to quit writing on me? Close the ink. Let me see if it writes then. Nope, it's going to be difficult. N is going to equal 11. So on here, we are going to use a 0.05 level of significance. Again, because it's an equal and a not equal, we're using the two-tailed test. And so the first thing I'm going to do is go ahead and go over on my table and find what my critical value is going to be. This is going to be difficult because my computer decided not to work right, but we'll get her to go. In this case, we said n was equal to 11. I got to turn my pen back on here. If n is equal to 11, it doesn't want me to write. I'll fix the computer. All right, let's see if it writes now. If n is equal to 11, there we go. And I was using a 0.05 level of significance on a two-tailed test. My critical value going to be 11. So my critical value is 11. Again, I have to clear this out and go back to our Word document, and then hope my pen tool wants to work. And so we said the critical value was 11. On our test statistic, again, we're going to get rid of the 0, negative, 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 positive, negative, positive, negative, positive, negative, negative. We've got 1, 2, 3, 4, 5, 6, 7, 8 negatives and 1, 2, 3 positives, which was our 11. That equals our n value. So again, we want to put them in order, ignoring the sign on there. So our smallest value here is going to be 2.5. Our next value, we have a 3, and then we have a 4. If we keep going on there, we have a 4.5 and a 5.5. Whoops, that was supposed to say 5.5. I'm just going to scribble it out because my eraser's not going to work. 4.5 and 5.5. Oh, I skipped some numbers. I am going to have to erase, but that's not going to work. Let's see if I can get it to erase. There we go. Let's go back. Okay. I better just X them out as I go. We have a 2.5. Turning my pen back on, hopefully. We said we had a 3, a 4, and then we have 2 5s. A 5 and a 5. Oops. I got my 4.5 already down there. And then I have my 5.5. And then I have 1, 2, 3 8s. And I have a 9. I think I got them all written down. Whoops. Turn my eraser back on. Now that I have them all written down. And my pen back on. So in this case, if I got them all in order and I have all my numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I should have them all because n was equal to 11. I now have them ordered disregarding the sign, pretending they're all positives. So this one would have a rank of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. On the numbers that repeat, we have to average. So in this case, I have 2 5s. I'm going to take my 5 plus my 6 divided by 2 and give them each a rank of 5.5. On my 8s, I have 3 8s. So I'm going to take 8 plus 9 plus 10 and divide it by 3. 8 plus 9 plus 10 divided by 3 happens to give us a value of 9. So each of these is going to have a rank of 9. And each of these is going to have a rank of 5.5 instead. So now we are checking. The lower number between our positives and our negatives was 3. So I'm going to use the 3 positive numbers from my list. The 3 was positive, the 9 was positive, and the 4 was positive. I'm going to use the ranks of each of those numbers. So 3 had a rank of 2, 4 had a rank of 3, and 9 was on this list, had a rank of 9. So the value for my test statistic, the rank of the 3 was 2, the rank of the 4 was 3, the rank of the 9 was 9. I'm going to add 2 plus 3 plus 9. If I do, oh, wait a minute. Ignore me. I used the wrong number here. Hopefully you were sitting there going, hey, that's not the right number. I was doing 8. All the 8s had a rank of 9. I wanted to do the 9. I should have used that number there. So going back to my test value. My 3 had a rank of 2, my 4 has a rank of 3, and my 9 has a rank of 11. I should have used an 11 there. I tried to use the 8 instead of the 9. So the 9 has a rank of 11. If I add all those together, 2 plus 3 plus 11, 5 plus 11 would be 16. So now that I have the value of my test statistic is 16 and my critical value is 11, we know that 16 is greater than 11. Since my test value is greater than my critical value, I am going to accept the null. Again, my null statement was that it's equal. My alternative one is not equal. This is my true statement. So, can we conclude there's a difference? No, we're saying that they're equal, that there is no difference. So, on the Wilcoxon signed rank test, you have to put all your numbers in order, ignoring the sign, rank them, and then average the rank if there is more than one value repeating. To find the test value then, we use the rank of each of the values of whichever is lower. So in this case, the 3 positive numbers. Then we can compare them just like we did before.